So, welcome to lecture series on nonlinear programming. In the last lecture, we have seen about quadratic programming problems. We have seen that how can we write Kkt conditions for a given QPP, and the Kkt condition will be sufficient if Q in the objective function is positive semi-definite matrix. Okay. Now, let us discuss the same thing by an example. Okay. Suppose we have this problem. Minus 2x1 x2 minus 6x1 minus 8x2 subject to, we have only one constant here, 2x1 minus x2 less than or equal to 13 and x1 x2 non-negative. Okay. So, we will try to solve this problem. There are different methods to solve a QPP. One method is Wolf's method. We will see what Wolf's method is and try to solve this problem using Wolf's method. Okay. So, first it is a quadratic programming problem because involved objective function is quadratic and all constants are linear. So, it is a quadratic programming problem. Now, what is Q here? Q is 1, 2, minus 1, minus 1. If you check for this Q, then D1 is 1, okay, 1 cross 1 matrix, determinant 1, and D2 is nothing but determinant of this 1 minus 1 minus 1 2, which is 2 minus 1 and again 1 greater than 0. So, this Q is positive definite and hence the function f is convex. Okay. Function f is convex because Q is positive definite and hence the function is a convex function. So, it will be a convex programming problem. So, the Kkt conditions which we obtained become sufficient. Okay. So, what will be the Kkt condition for this problem? So, to write Kkt condition, either we apply those conditions directly which we discussed in the last class, or we can first define a Lagrange function like this L, which is f is x1 square plus 2x2 square minus 2x1 x2 minus 6x1 minus 8x2 plus multiplier corresponding to this constant is suppose u. For this suppose v1, for this constant suppose v2, then u time the first constraint 2x1 minus x2 minus 13 minus v1 x1 minus v2 x2. So, this we write as Lagrange function L. Then what is del L by del x1? It is 2x1 minus 2x2 minus 6 plus 2u minus v1 equal to 0. What is del L by del x2? It is 4x2 minus 2x1 minus 8 minus u minus v2 equal to 0. So, these are the first Kkt condition. Okay. You can obtain directly also by writing that condition. Okay. Then now, by remembering that condition, other conditions are the feasibility condition, that is 2x1 minus x2 plus s is equals to 13 and x1 x2 non-negative. Of course, u v1 v2 also non-negative, and one more condition, that is ui si equal to 0 for all I and vj xj equal to 0 for all j. So, here it is u into s equal to 0, only one constant and one variable is involved, and v1 x1 is equals to v2 x2 equal to 0. So, these are the Kkt conditions for this problem. Okay, for this problem these are Kkt conditions. Now we can readily see that these Kkt conditions, except these conditions are linear. So, we can apply some method of linear programming problem to solve this particular problem. So, before solving this problem, let us recap on linear programming problems. Okay. Let us see how we can solve a linear programming problem, and then we will come back to this problem itself and we will see how to solve this problem. Okay. So, first we will come back to go to LPPs. Okay. So, this is the Kkt condition we have already seen, okay, for this problem. Now, what are linear programming problems? We already know that if objective function and all constants are linear, so such problems are called linear programming problems. Here if all constraints are of equality type, we make it an equation. If all constraints, we make it an equation keeping right hand side non-negative, then such problems are called standard form of LPP. Okay. Here xi's are called decision variables and these coefficients are called cost of xi. Okay. Suppose let us consider the simple problem of two variable problem 2x1 maximizing of 2x1 plus 3x2 subject to these linear constraints. So, this problem we can solve graphically also, very readily we can solve this problem graphically. Let us see how. What is the first constraint? First constraint is, what is the problem? Problem is maximizing z equals to 2x1 plus 3x2 subject to, it is 2x1 plus x2 less than or equal to 4 and it is x1 plus 2x2 less than or equals to 5 and x1 x2 non-negative. So, we already know how to solve this problem graphically. It is very simple. You can simply see here you have one when x is x1 axis, one is x2 axis. You can take first inequation as an equation. First equation is 2x1 plus x2 equal to 4. When you take x2 equal to 0, x1 is 2, x1 is 2 and x2 is 0. When x1 is 0, x2 is 4. So, it is 1, 2, 3, 4, it is 4. So, this is the first constraint, that is 2x1 plus x2 equal to 4. And when you take 0 comma 0, then 0 comma 0 satisfy this constraint. So, shade is toward origin, then shade is toward origin. Now, again for the second constraint is x1 plus 2x2 equals to 5. When you take x2 equal to 0, x1 is 5, x1 is 5 means 3, 4, 5 this point. And when x1 is 0, x2 is 5 by 2, x1 is 5 by 2, that is here. So, this is second constraint, that is x1 plus 2x2 equal to 5 and this is the point of intersection. So, what are the, of course, when you take 0 comma 0 satisfy this constraint, then shading is toward origin. You shade towards origin, this is shading and it must be in first quadrant also. So, this is a feasible region. This point is 2 comma 0, this point is 0 comma 5 by 2 and this point intersection of these two which is 1 comma 2. You can see 1 comma 2 satisfying both the constraint. So, this is a feasible region. Feasible region is a convex set. It is very simple to see because all constraints are linear and hence all conditions are convex function and the set comprising of all the linear constraints and I mean convex functions is a convex set. So, it is a convex set simply. We can show it also that feasible region of LPP is a convex set. Okay. And in LPP optimal solution always be obtained at one of the vertex if feasible region is bounded. Now, here value of z at origin is 0, value of z at 2 comma 0 is 4, value of z at 1 comma 2 is, it is 2 plus 6 that is 8 and value of z at 0 comma 5 by 2 is 15 by 2 that is 7.5 and we have to maximize z. So, maximum is obtained at this point which is 8 out of all these 4. So, the optimal solution we can readily see that the optimal solution is x1 equal to 2, x2 equal to x1 equal to 1, x2 equal to 2 and z equal to 8. So, this is the optimal solution of this problem. Okay. So, this is a graphical approach to solve a LPP. Now, come to this problem, the same problem and we will try to solve the same problem using simplex technique, simplex method. How can we solve using simple? Let us see. This is an inequality which is less than or equal to type. So, to make it an equation, we add a variable here in the left hand side, because this quantity is less than or equal to this, that means we have to add some non-negative value here to make it an equation. Okay. So, this you can write it as 2x1 plus x2 plus s1 equal to 4. Suppose that variable is s1. So, we call that variable as slack variable, it is a slack variable s1. Okay. Here also x1 plus 2x2 plus s2 equals to 5, and all variables are non-negative. All variables are non-negative. Okay. If we have greater than or equal to type constraint, suppose this constraint we are having 3x1 plus 2x2 greater than or equal to 6. So, to make it an equation, we subtract a variable which we call as surplus variable. Okay. So, this we can write it like this, 3x1 plus 2x2 minus s1 equal to 6, and this s1 here is called surplus variable. Okay. To make it an equation, because first of all in simplest method we need to write the problem in the standard form. For the standard form, all inequalities must be quotient, and right hand side must be non-negative, and all variables must be non-negative. So, this is the standard form of LPP. The standard form means all constraint must be of equation, all variables non-negative, and right hand side must be non-negative. Okay. Now, how can we start our process and how can we try to solve this problem? Let us see here quickly by see this problem. So, we make a table here. Let us see how we can solve these problems. How many variables we are having? 4 variables, x1, x2, s1, s2. So, 4 variables we are having, x1, x2, s1, s2. What are the matrix? I mean coefficient of x1 2 and 1, coefficient of x2 it is 1 and 2, s1 is 1 0 and s2 is 0 1. Okay. Now, in the simplest method, we first start with that variable, those variables which make identity in the first table. Now, here we are having identity corresponding to these 2 variables. So, we start with s1 and s2. We start with s1 and s2. And what is the right hand side? Right hand side is 4 and 5. 4 and 5, that is solution. Solution is 4 and 5. Okay. Now, writing this means s1 and s2 are variables whose values are 4 and 5, and all other variables are 0. So, these 2 variables are called basic variables, and all other variables which are at 0 level are called non-basic variables. Okay. So, here s1 is 4, s2 is 5, and x1 and x2, the remaining variables are at 0 level. So, if you see, if x1 and x2 are 0, then s1 is 4, x1 x2 and 0, then s2 is 5. So, s1 is 4 and s2 is 5. Okay. What are the cost of s1 and s2 in the objective function? In the objective function, s1 is not here, the cost is 0. In the objective function, s2 is also not here, the cost is 0. CJs, the cost in the objective function, cost is 2, cost is 3, cost is 0, cost is 0. Okay. Now, how we will start our iterations? How we will start our process? We first find relative profits. What relative profits are? Relative profit means, you see, we have to maximize this objective function subject to these conditions. Okay. And in each iteration we want to improve the solution. Relative profit means change in the value of z per unit change in the value of variable. Suppose you increase the variable x1 is in 0 here, x1 is equal to 0 here. Suppose you change x1 from 0 to 1. So, what will be the value, what will be the change in the value of z? That is relative profit. Okay. Similarly, you would observe that if you change x 2 from 0 to 1, then what will be the corresponding change in the value of z? Okay. If it is positive, if the change is positive, that means if you enter that variable, the value of z will increase definitely, because if you are increasing this variable from 0 to 1, the value of z increases, the value of relative profit is positive, that means z increases. So, you have to enter that variable. Okay. So, how to find relative profits? So, I am not going into much detail here, I am simply finding the relative profits. So, relative profit is nothing but you simply multiply this CB into xj, 0 into 2 plus 0 into 1, that is 0, okay, and this minus this, that is minus 2. This is negative of relative profit. Relative profit is 2, okay, 2 units. Again this into this plus this into this is 0, 0 minus 3 is minus 3, 0 into 1 is 0, 0 minus 0 is 0, then 0 is 0. Okay. So, why this, that we are not discussing here? This is 2 units, it is 2, I mean if you take plus 2. So, that is relative profit corresponding to x 1, and relative profit means if you change the value of x 1 from 0 to 1, the net increase in the value of z is 2 units. You can verify also. If you again increase x 2 from 0 to 1, the net change in the value of z is 3 units. So, this is giving higher value than this, because if you increase x 2 from 0 to 1, the increase in the value of z is 3 units. So, of course, if you enter x 2, then the value of z will increase much higher than if you enter variable x 1. So, you enter x 2. Entering x 2 means now x 2 will become a basic variable, x 2 will become basic variable, and out of these 2 basic variable, one will go to non basic variable. Is it okay? Now, out of these variable, which variable will leave the basis, that will be decided by minimum ratio rule. What is that? It is solution upon that entering column, 4 upon 1, 4 upon 1 is 1 is 4, and 5 upon 2 is 2.5. The value which is minimum will leave the basis, and this rule is called minimum ratio rule, and the intersection of these 2 arrows, this point, is called pivot element. Okay. Why we are following minimum ratio? Because if we leave this and not leaving this, then the feasibility condition will be disturbed. Feasibility condition means both should be non-negative, because all variables must be non-negative. We have to maintain that condition, all variables must be non-negative. If we are not following minimum ratio rule, then feasibility condition will be disturbed. Okay. So, now we will make the next table. How to make the next table now? You see, it is S1 and it is X2, okay, and you make 1 here by dividing with 2, that is 1 by 2, 1, 0, 1 by 2, 5 by 2, and make 0 here with the help of this, that is make identity corresponding to the basic variables always. Here we already have an identity corresponding to basic variable, and here corresponding to x1 identity is not there. So, make identity corresponding to the basic variables with the help of pivot element. You divide by 2 here, that is if it is R1, R2, R3, R3 you replace R3 by 2, and in R2 you take R2 minus 1 by 2 of R3, this minus half of this, this minus half of this is 3 by 2, this minus half of this is 0, this minus half of this is 1, this is minus half, and this plus 3 by 2 times this. So, R1 may R1 you can take R1 plus 3 by 2 times R3. So, this plus 3 by 2 times this plus 3 by 2 times this is minus 1 by 2 is 0, 3 by 2 is 0. Okay. Now, what is the relative profit corresponding to x1? Is 1 by 2. What is the relative profit corresponding to s1? Is minus 3 by 2. It is simply negative of relative profit. It is negative of minus 3 by 2, that means if we entered it this variable, the value of z will decrease. Now, it is 1 by 2 relative profit corresponding to x1, that means if we enter this this variable, again the value of z will increase than what we have obtained in this table. Okay. So, when this process will continue till all this relative profits, all these values are greater than equal to 0. Greater than equal to 0 means relative profits are less than equal to 0. So, you can verify your calculation from this table itself. You see, in the first table we are obtaining these relative profits and this thing, it is minus 1 by 2 and it is 1. Let us see it is 1 or not. S1 is 0, because this is 3, this plus 3 by 2 times this plus 3 by 2 times this is 3 by 2. Here we have mistaken. Okay. Now, again we will apply minimum ratio, and here it is this minus half of this. So, this minus half of this is 4 minus 5 by 2, 4 minus 5 by 2 is 8 3 by 2. Okay. Now, now this enters, because this relative profit is positive. Okay. And what is the minimum ratio? This upon this is if you take here, then 3 by 2 upon 3 by 2 is 1, and this is 1 by 2 upon this is 5 by 2 upon 1 by 2 is 5. So, this is minimum. So, this will leave, and this is the pivot element. So, again you will complete a table, you will make 1 here by multiplying the entire row by 2 by 3, make 0 here with the help of this minus 1 third of this in the entire row, and this plus 1 third of this make 0 here. So, you will complete a table in this way. So, you will obtain this table, and what is the optimal solution we have obtained, that is x1 equal to 1 and x2 equal to 2, what we have which we have also obtained using graphical approach 1 and 2. Okay. You can easily check, and you can also verify that in each table you are goes on increasing your value of z. You see, in this table value of z is what? Value of z is 0, because x1 x2 both are 0, x1 x2 are 0 means value of z is 0. In this table x1 is this, x2 is this. So, x1 is 0. If x1 is 0 and x2 is 5 by 2, that is z is 15 by 2. So, here z is 15 by 2. And the last table, in the last table, if you see the last table, then the last table x1 is 1, x2 is 2. So, what will be z? Z is 8. So, in the last table z is 8. That means in each table the value of z is increases, value of z increases, and the last table is an optimal table, because all these z, capital Z, are greater than or equal to 0 and feasibility condition is maintained. So, feasibility condition definitely maintained because of the minimum ratio rule. Okay. And this all are greater than or equal to 0, that means this is an optimal table, and x1 is 2 and x2 is 2 is an optimal solution. Okay. So, this is one of the illustration of simplex algorithm, because we have to apply this algorithm in Wolf's method also. So, that is why I have explained it here. Now, the same problem of LPP in the for 3 variable problem can be solved in the same way. You can easily see. Now come to our Wolf's method. We are solving this problem basically, and for this problem we have already write Kkt conditions. What are Kkt conditions? Kkt conditions are 2x1 minus 2x2 plus 2u, u or u1 minus v1 equals to 6. The second constraint is minus 2x1, then it is plus 4x2 minus u1 minus v2 equal to 8. Then it is 2x1 minus x2 plus s1 equals to 13. All variables non-negative, and u1 s1 is equals to v1 x1 is equals to v2 x2 is equals to 0. So, these are the Kkt conditions which we obtain for this QPP. Okay. Now, how to solve this problem? Let us see. So, first accept this condition, all constraints are linear, okay, and this is u1 s1 v1 x1 v2 x2 equal to 0. This condition make this problem non-linear. Okay. Now, to apply a simplex algorithm, okay, we first need an objective function, number 1, and we first need variables such that corresponding to which we have identity in the first table. Okay. You see here it is minus v1. So, coefficient of v1 in the entire problem is minus 1 0 0, coefficient of v2 is 0 minus 1 0. It is in the standard form, okay, it is in the standard form, okay, but we are not having identity corresponding to the variables, but for S1 we are having, S1 it is 0 0 1, yes. For S1 we are having identity, one column of identity matrix. Okay. Now, first how we will introduce identity, and then how can we formulate objective function. So, what we do, we add variables which we are calling as artificial variable corresponding to the first and second constraint, because here we do not have identity corresponding to these constraints. So, we deliberately introduce two more variables here, and those two variables are called artificial variables. Okay. Okay. Now, if you see A1, A2 and S1, we are having identity corresponding to these constraints. If you see A1, the coefficient of A1 is 1, 0, 0, A2 0, 1, 0, S1 0, 0, 1. So, now we are having identity corresponding to these three constraints, these three equations. Okay. But this was not our original problem, we have changed the problem by adding artificial variables, by introducing two more variables in the problem. Okay. Now, we construct our objective function as, and we are letting A1 A2 also non-negative, okay, all variables non-negative. Now, we want that these two variables must leave the basis, because must leave means both become 0. If both become 0, then only we get back to our original problem. Our original problem is without A1 A2, okay. So, that we will obtain without A1 A2 only when A1 A2 both are 0. So, we construct our objective function like that only, we construct our objective function like minus A1 minus A2. Why this? Because you see A1 A2 both are non-negative. So, it will be maximum only when both are 0. It will be maximum only when both are 0, and as soon as both are 0, we get back to our original problem. What we need basically, we need a point x1 x2 will satisfy all these conditions, that will globally minimize our problem, that will be the optimal solution of that problem, of our problem. Okay. And solving this problem is not an easy task, I mean it is not so easy, because we are having this condition also. Okay. So, to apply a simplex algorithm, we add new variables which we are calling artificial variable and adding a objective function like this, because as soon as this will be maximum only when a1 a2 both are 0, and as a1 a2 both are 0 we get back to our original problem. If suppose a1 a2 are not 0, a1 or a2 not are 0, so that means our problem is infeasible, our problem has no solution, because a1 a2 are not becoming 0, that means we are not getting back to our original problem, that means our problem is infeasible, our problem is have no solution. Okay. So, now we have objective function which is linear, these constraints, and we will apply the same simplex algorithm to solve this problem. Now, how we can solve, let us see here by the tables. Now, you can easily construct this table. You see a1, a2 and s1, this form identity in the first table, so they can be act as a basic variable in the first table. All other variables are at 0 level. So, a1, the value of a1 is 6, value of a2 is 8, value of s1 is 13 in the first table. Okay. Again you will find capital Z which is which are negative of relative profits, okay, in a usual manner as we have already discussed. Now, this relative profit is 2 units and this relative profit is 1 unit. All other relative profits are negative. You see, this is simply negative of relative profit. So, simply multiply by -1 and then you can see what are relative profits. So, you will either enter x2 or you can enter u1. If you enter x2, now what additional thing is here besides simplex algorithm, what additional thing is here? You see, we have extra condition also that u1 s1 should be 0, v1 x1 should be 0, v2 x2 should be 0. That means that both the variables u1 and s1 or v1 x1 or v2 x2 be not there in the basis simultaneously. Okay. What does it mean? You see, here it is most negative, so it is entering. The complement of x2 is what? v2. v2 is not there in the basis in the first table. In the first table v2 is not there. Okay, v2 is not there in the basis. That means v2 is at 0 level. v2 is equal to 0. So, if we enter this variable, then v2 into x2 equal to 0 is remain satisfied, because v2 equal to 0. So, we can enter this variable, enter this, leave by minimum ratio rule, only this will be counted because this is positive. For minimum ratio we take ratio only for the positive column entries. Okay. So, this is 4, this is 8 upon 4 is 2. So, this will leave the basis. You consider next table, this is pivot, you make 1 here by dividing with 4, you make 0 here, you make 0 here, become 0 here with the help of this pivot element. Now you consider next table. Now, this is most negative, -3 by 2. Now, if you enter this u1, what is the complement of u1? s1. u1 s1 must be 0. Complement means u1 s1 equal to 0, the complement of u1 is s1. If you enter this u1, s1 is already there in the basis. So, u1 into s1 may not be 0. We have to maintain that condition, u1 s1 must be 0. It will be possible only when only one of them is in the basis, then only, because then the other variable will be 0, then only we will be having u1 s1 equal to 0 or v1 x1 equal to 0 or v2 x2 equal to 0. Okay. So, we can't enter this variable because s1 is already in the basis. Now, the next is x1. So, enter this. If we enter x1, what is the complement of x1? v1. Is V1 there in the basis? No. So, yes, we can enter x1, because V1 is not there in the basis means V1 equal to 0. If V1 equal to 0 means V1 x1 equal to 0 is condition is satisfied. So, we can enter x1. We can enter x1 again by minimum ratio. 10 upon 1 is 10, it is negative, so leave it. It is 15 upon 3 by 2, that is 10. You can now leave any one, because minimum ratio rule is value is same. So, you can leave any one. It is better to leave artificial variable. Okay. So, you leave artificial variable, construct the next table, and next table is the optimal one. So, this is an optimal solution. X1 is 10, X2 is 7. So, X1 10, X2 7 is an optimal solution of this problem. You can easily check what are the values. X1 10, X2 7, and S1 is 0, and all other variables are obviously 0. U1, V1, V2 all are 0. Now, if we take our original problem here, again if you take the original problem, because artificial variable leave the basis, now these definitely satisfy all the constraints. You see 20 minus 14, 20 minus 14 is 6, and it is, these are all 0 equal to 6. It is minus 20 plus 28 is 8, all are 0. It is 20 minus 7 is 13, 13 plus 0 is 13. All variables are non-negative, this condition is satisfied. So, this point satisfy all the constraints, and hence solve our problem, our QPP. So, it is, we have to apply the simplest algorithm with the additional condition that if we enter a variable, its complement must not be there in the basis. That is the only condition we have to take care of. If the condition holds, so enter the variable, leave by minimum ratio rule, complete table, and apply it till you obtain the optimal solution. Okay. So, that is all for Wolf's method, and you can solve such type of problems using some softwares also, which is freely available. So, thank you very much.